Hello again. So in this video, we are on a new topic, and that is systems of equations and inequalities. And the first thing that I wanted to show you guys is one of the resource pages, additional resource pages that you have in the back of your workbook. It's called Systems of Equations and Inequalities Summary Sheet. So I wanted to point this out to you, that it might be helpful to you. It's on page 193 for me, but I have a little bit earlier version of that workbook. So if you guys just search around, and you also have a table of contents, so kind of search for it, you'll be able to find this. You can see that it's broken down into systems of equations, and then there's a bit of information on the bottom for systems of equalities. And I'm not really going to go over this sheet right now, other than to say that we are going to be talking in this video and the next couple of videos on different ways that we are going to solve systems of equations. In this video, we'll talk a bit about graphing. That's one way to solve a system. And then substitution method and elimination method are both algebraic ways. So we're using our math processes to solve these systems. And I will definitely talk a lot more about that coming up. All right, so let's take a look at this page here, which is just some notes, some kind of background information about systems. So let's talk a little bit first about what exactly is a system of equation or inequality. So the word system means that we've got two or more. So we've got two or more equations or inequalities that share two or more unknowns. Okay, in this particular class in Math 98, we're going to be talking about systems with just two variables. So we've got an x and a y, or a m and an n. But you can have systems that have multiple unknowns and multiple variables. Now, the solution to a system, so to a system of two equations, is an ordered pair. It's an ordered pair. It's an x and a y that make both of the equations true. So this is important too, that whatever that ordered pair is, let's say we call it 1, 3, x is 1, excuse me, y is 3. When we plug in those numbers to both of those equations, it has to be true for both of them in order for that solution to be correct. On a graph, the solution is the intersection of both of those lines. So it's the point where they cross. And like I just got through saying, the x and y value where those lines intersect have to satisfy both of the equations or make them both true. Now, systems of inequalities are basically just the same as a system of equation. It's just that systems of inequalities, of course, has inequality signs rather than equal signs. We will be talking more about systems of inequalities in another video. I'm going to be concentrating on systems of equations in this video. But I wanted to point out the difference here in terms of the solution to both of these. So we just got through saying system of two equations is an ordered pair. System of two inequalities is any point within a region of overlap. So as you can remember, in previous unit, Unit 13, we were graphing inequalities. And of course, when we're graphing an inequality, we shade a region, whether it's above or below the line. Well, you can imagine then if you have two inequalities, we're shading two different regions. And so what we're really interested here is this overlap. We want to know where is the overlap of those shaded regions, and that is the solution. So you can see that it's not just one point. There are, an infinite number of points really in a shaded region. And of course, the point that we choose in that shaded region, of course, has to make both of those inequalities true, just like the system of equations. All right, now we talked just a moment ago about different ways that we can solve systems of equations. Graphing is what we're going to be talking about today. And then, of course, the two algebraic methods are elimination and substitution, which we are going to talk about coming up here pretty soon in another video. All right, so in order to really talk about these solutions to these systems of equations, we need to talk a bit about some terminology. You guys are going to be talking or be seeing on NROC and being exposed to the terminology either consistent or inconsistent system. And what I want you guys to think about when you see that is, does it have a solution? Does this system have a solution? That's the question that you ask. If it does have a solution, it's consistent. If it doesn't have a solution, it is inconsistent. Okay, so that's kind of how you would break down that terminology. Okay, now next is this idea of dependent or independent systems. And the question there are the two lines the same or are they different? If you have the same line, it's a dependent system. Okay, the lines actually depend on each other. They're lying right on top of each other. They depend on each other for their solutions. If they are different, so different lines, they're considered an independent system. Okay, because those lines are running in different directions. They're independent of each other. Now, all of that information can get really confusing, and definitely not going to be testing you on that terminology at all, but it is something that you see, when we're talking about these systems. It's something that you will see in the future. So we need to kind of bring it into what we're learning in this class. And I'm going to try to focus in really on what is the most important parts about this idea of consistent, inconsistent versus independent, dependent. So we have three types of solutions. Okay, we have three types that we're really going to be talking about. One type of solution is just simply what we call a one solution. And that really just means a one intersection. Okay, it's basically, if we were to draw a little sketch here. Okay, it's actually saying that we've got one line here, and let's say we've got one line here. So this is our system. This is one equation and another equation. And right here, let's just call this, just for grins, let's call this 3, 3. Okay, there's one intersection, one solution. And we call this consistent because it has a solution, right? And we call this independent because these lines are different. You can see they're running in different directions. Okay, so the second type of solution is what we call an infinite solution. And an infinite solution means that the lines are exactly the same. Okay, so you guys can imagine, you probably don't really even need a sketch of this, but so let's say we have a line going this way. That's one equation. And we have another equation that literally is exactly the same line. So you can see there's an infinite number of solutions on here, right? I mean, there's solutions all over this line. And of course, it goes to infinity in both directions. So we know that it is definitely a consistent system because it has an infinite number of solutions, and it is dependent because it's the same line. All right, and finally, we have what we would call a no solution. And a no solution is just simply parallel lines. And if we just think about the meaning of the word parallel, right, we know that parallel just means that the lines are running in the same direction. They will never cross each other. So if we come back up here to this idea of the solution to a system of equations being the point of intersection, well, parallel lines don't ever intersect. Therefore, it is an inconsistent system. There is no solution, and they're different lines, so it's independent. So that's kind of how we talk about these two, the two ideas of inconsistent, consistent, and dependent versus independent. Now, what do you guys really need to know from this? This is kind of where I want to get to here. This is what I'm looking for. This is what I want you guys to really be thinking about in terms of all of this. Not really like, oh, we label this, inconsistent, label that dependent. I want you to consider what the solution types look like. Obviously we can see here, if we look at the 3 different graphs here, they look very different from each other, right? So I want you to consider what the graphs should look like. Okay, that's important. And consider then in the equations what those would look like. How do the slopes of both of those equations compare to each other? Are they the same slope or are they different slopes? How do the y-intercepts differ from each other? Are they the same or are they different? Okay, so this is the type of question that you're going to be asked. In fact, on the final exam, I will ask you to create a system that has particular parameters. For example, if I were to ask you to create a system with one solution, okay, we know that, of course, with all these, we're going to have 2 equations because that's what our system, in this particular class, that's what our systems of equations consist of, our two equations. But we know that those equations have to be different, right? Therefore, we know that the slopes are different from each other. Okay, the slopes have to be different from each other. We can see in our example up here, our slopes are, in this example right here, our slopes are very different from each other. Our y-intercepts could be the same, so the b could be the same. They could actually cross right at the y-intercept, right? If I had moved this line down right here, this red line, let me just go back up here and do that, right? Let's say that these lines crossed right here instead. Well, our b would be the same, but you can see that our slopes are very different from one another, and that results in this idea of one solution. Okay, so you need to kind of be thinking about what that would look like and then create 2 equations, excuse me, 2 equations that would result in that effect. Secondly, thinking about maybe what an infinite system might look like. Okay, let's look at that. Well, of course, we've got 2 equations. An infinite solution, if we look up here, we can see, remember, they're the same darn line, right? So these equations are the same equations. Therefore, we know the slopes are the same and the y-intercept is the same. Now, they might be presented in a little bit different way, but when you simplify the equations down, you'll find out that they're exactly the same. We're going to do an example of that in a little while. All right, thirdly, what does a no solution look like? What would a system look like that you were creating that has no solution? Well, we've got our 2 equations, of course, we know that, and we know that the idea here would be that the slopes are the same, but the y-intercepts have to be different. Let's look at that right here. So we've got our no solution right here. Okay, we know that those lines are parallel. So of course, when we have the same slope, that is what results is 2 parallel lines, right? These are stair-stepping at exactly the same rate, right? Same slope. However, they have 2 different y-intercepts. They can't have the same y-intercept, otherwise they would be exactly the same line. Oops, why is that not working here? All right, there we go. You can see that they cross the y-intercept at different places. If they didn't, they would be exactly the same line. So this is what I want you guys to be thinking about. Okay, this is what is going to be important, is the knowledge of what these 3 different types of solutions look like, and how do I create equations thinking in terms of my m and my b, the slope and the y-intercept, to make them the type of solution that that you're required to come up with. All right, guys. So what I'd like to do next is just go right to our worksheet here, and let's do some examples, kind of walk through examples of what we've been talking about. All right, so example number 1, right here we're actually, just to kind of remind ourselves, right now we're talking about systems of linear equations, okay, not inequalities. And example number 1 says determine whether -4, 7 is a solution of the system. So what they're really asking us is, at this excuse me, at this point, -4, 7, is this where these two lines cross each other, right? Well, we don't have a graph, so we can actually look at this just in terms of our algebra. Okay, so what we're going to do is just plug in these numbers. Of course, the -4 is our x, the 7 is our y. So we're just going to plug in these numbers. Let's try. So we've got -4 plus 7 equals 3. Well, -4 plus 7 is 3. So this one checks out, right? But we do know that we have to be careful. It's not a solution unless it makes both of the equations true. So we definitely have to double check the other equation as well. All right, so we've got -20 minus 7 gives me a -27, and that holds up as well. So yes, this is definitely a solution to this system of equations. If it didn't work, if it worked for one of the equations but not the other, it would not be a solution. All right, so let's go down here, and here we're asked to solve each system graphically. Okay, this was the first way. Remember that we are going to be learning about how to graph these things. So we're solving each system graphically, and then check the solution in the given equation. And then down below, we're asked to visit this idea again, remember, of consistent or inconsistent, dependent or independent. So we'll get there in just a minute. So basically, the steps here for solving by graphing is we want to start by graphing the equations, okay? And we know how to do that pretty easily. Now, you guys have choices, of course, in terms of how you graph your equations. You can rewrite them so that they're in the form, of course, of y is equal to mx plus b, and then you can graph based on that equation. You can see in example A, these are set up really, really well to graph by intercepts, right? Because our x and our y are both on the same side. So I'm going to just do that. We're going to call this guy equation number 1. So I'm going to come down here and do my intercept table for equation number 1. All right, when x is 0, I need to find y, and when y is 0, I need to find x. All right, so let's do it. So we've got y is equal, or y minus 0 equals 1. Well, that's pretty easy. Y is equal to 1. Okay, and 0 minus x equals 1. So that means I've got a -1 here. I'll just stick a -1 in there. I know that I've got to divide that. So x is -1. Okay, so these are actually my points, right? I can just put little parentheses around here if I want. I've got my coordinates right there for equation number 1. So my y-intercept is right here at 0, 1. My x-intercept is right here at -1, 0. Okay, so I'm going to graph or sketch my line here. Okay, and I can do the same for the second as well. Let's choose a different color. Let's go with blue. Okay, I'll do my XY table there. All right, so we've got y plus 0 equals 3. Well, we can see easily that y would equal 3. And 0 plus x equals 3. Well, that's pretty easy too, right? X is equal to 3. So our y-intercept here is at 0, 3. Our x-intercept is at 3, 0, if we were to see these as coordinates. And I'm going to just 1, 2, 3. So I want to make sure that I'm going through the lines as I should, since I don't have my straight edge on my iPad. All right, so looks to be the solution right here. And remember that we write our solutions as an ordered pair. I actually did not mention that before, and that's actually pretty important. We write our solutions as an ordered pair. So the solution here would be 1, 2. All right, let's take a look at this idea of consistent, and well, we'll come back to that. Let's come back to that in a minute. All right, I'm gonna clean this up just a tinch, give us a little bit of room. Let's go on to B. So you notice B is already written in terms of our y is equal to mx plus b. So I'm going to graph these in a little bit different way. I'm not going to use intercepts because my x and my y are on different sides of the equation. Make it a little bit easier for me just to graph using the equations. Now remember, when we're graphing using the equations, our first step is to, sorry guys. Our first step is to plot B. Our second step is to use our m, or our slope, to plot another point. It's a nice, really swift way to graph. So in equation number 1, my y-intercept here is at 0, 5. And my slope is negative 3 over 1. Right, so I'm going to go down 3 on my y, so there's 1, 2, 3, and a positive 1 on my x. I kind of like to put a couple of points instead of just one more. It just kind of makes me, I guess, gives me the confidence that I'm graphing it correctly. Okay, so this is equation 1. I didn't label those over here. I should always do that. This is my equation number 2. All right, let's do the same for equation number 2. Looks like our y-intercept is at negative 2, so 0, negative 2. And I have the same slope. So if we're thinking about that, we have same slope but different y-intercept. Okay, we should be thinking about what that really would look like. Same slope, different y-intercept means these should look parallel, right? And this means that I can go down 3 once again and over 1, but it also means that I could go up 3 and then a negative on my run. Remember that negative 3 divided by 1 is the same as 3 divided by negative 1. So from this point I could go up 3. From the negative 2 I could go up 3, so 1, 2, 3, and then I could go negative. And you can see those points all fall in line with each other. So these are indeed parallel lines, right? So no solution is what we're coming up with here. We know the solution here we said was 1, 2 on A. There's no solution to parallel lines because they never cross. All right, let's check C here. Now you see on C, we definitely have a little bit of work to do. We have our x and y on their same sides. We could definitely work with our intercepts just in terms of how we graph these. But I can see that my equation number 2 could definitely be simplified a bit. So we see that we can find a greatest common factor here of 4. So let's just simplify this right off the bat. Make our lives a little bit easier. So we've got a 3y, or negative 3y, plus 2x equals negative 6. Okay, that's actually going to help us a little bit. All right, let's go ahead and set up our intercepts here. So I'm going to call this, oops, sorry, give me myself. So this is our number 2, x and y. All right, so if I put in a 0 for x, we can see that this whole second term will go out, right? I didn't leave myself enough room to do this. Right, I guess I'm gonna have to come over here a little bit. It's gonna be like a negative 3y is equal to negative 6, 3, negative 3, y is equal to 2. Okay, and we go here on number 1. Do an xy intercept table. Oops, I didn't do the other one. I gotta go back. What am I doing? What am I thinking? Sorry, guys. Let's just finish where we are. So if x is 0 here, we can see this is going to be 3y is equal to 6, and 6 divided by 3 is 2, right? And then vice versa, if we were to say that y is 0, we're going to have a negative 2x is equal to 6, and then when we divide by negative 2 on both sides, we're going to have a negative 3 here. Okay, so I have these coordinates here. I neglected to finish the first one, which I will do right now. Okay, so if y is 0, we can see this whole thing will be crossed out, and we would have a negative 3 here. Okay, so here's our coordinates here. What you can see is that these are going to be the same line, right? We can kind of see that as we are looking through here. So let's go ahead and plot these. We've got 0, 2, and negative 3, 0. Okay, let's go ahead and, whoops, that was a really bad line. Sorry, guys. And once again, 0, 2, and a negative 3, 0. Same line, right on top of the other one. So you can see that at first they did not, they definitely didn't seem that they were the same, but after we did a little bit of work on them, we can see that they are indeed the same line. Okay, so if you can remember from before what we talked about, when we have the same line, there are an infinite number of solutions, right? So that's the type of solution, because we know there is an infinite number of points that are at least that point of intersection that we would refer to. All right, guys, so let's finish this problem out by talking here about the consistent versus inconsistent first. Remember these two terms. Just ask us to consider, is there a solution? Right? That's what we're really thinking about here. So obviously in this example, this first example, we totally have a solution. So this would be a yes, this would be a no. So we have consistent here. And there is no solution in the second example, right? Those parallel lines never cross. So this is inconsistent. And on the third example, it's definitely consistent, because not only do we have one solution, we have an infinite number of solutions there, don't we? Okay, now the dependent or independent, remember, is really talking about whether we have the same lines, I should say, or different lines. Okay, if we have the same line, we're talking about dependent, right? Because they definitely depend on each other. Different lines are independent. Okay, these are different lines here in example A, so we're going to call this independent. Okay, and of course, parallel lines, those are same slope, but they're not the same equation because they have a different y-intercept. So they are different lines as well. But of course, we can see the same line are not different lines, so they're dependent. All right, guys. So let's move on. I'm going to skip over example 3. That's an application problem, and I'm going to be doing a separate video on the application problems. Okay, guys. So let's look at number 3, though. It says find the solution for each system of linear equations. And I'm going to try to iterate this now because I neglected to do that on the note page. I just realized, but remember that a solution, we always write, I'm going to write this down here, we always write this as an ordered pair. Okay, so what that really means is an x and a y. All right, so remembering that in a system of equations, the point of intersection is our solution. Means that the solution here would be at 2, 1. Okay, and if you take a look over here at the example number 4, looks like we're at -3, -2. -3 on our x, -2 on our y. That would be our solution. All right, guys, and you can, the other ones you can see, you would go through and do those. That's pretty straightforward. Solve the following systems by graphing. Okay, so if we were to do this, I know we just did these examples like these just a moment ago in the examples. So I'm not going to, I think I'm not going to do number 8. It's very similar to one of the other ones that we did. So I'm not going to do number 8, but I did want to take a look at number 9 here. Just another example, one more to work with here. So the reason I wanted to do this one is kind of a reiteration of what I had just talked about before, is that sometimes our equations don't look the same, but once we do a bit of work on them to do some simplifying, we find out that they are the same. So if we look at the equation on the right, first of all, we can see that we can factor out a greatest common factor from every single term. So I'm going to just start by doing that, see if we can get it to look similar here. So we've got a 3x minus y is equal to 4. And you notice that this one is written in standard form, right? So we want this one to look the same way. So we're going to rewrite this to move everything over to where it should be. So we've got a -y is equal to -3x plus 4, oopsie, minus 4. And we got to get rid of this -1 here. So we've got a y is equal to 3x plus 4. Oh my gosh. Minus, oh, it was plus, duh. All right, minus 4. And voila, we have the same line, exactly the same line. So we can, guess at the fact that this is going to be an infinite solution, right? Well, obviously, we're going to be having both of these graphed on the same line here. Gosh, I can't even talk today. What the heck? Number 1, we're going to plot our y-intercept, and we're going to use our slope, which is 3/1. We go 1, 2, 3. Oopsie, 1, 2, 3, 1. Wow, I'm having trouble here, aren't I? 1, 2, 3, 1. 1, 2, 3, 1. Right. Other one's right on top of it. There's really no big surprise here. Da 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 da. Infinite solution. All right. Think you guys get the picture. I did want to talk about these last three problems here. This kind of goes along with what I was talking to you about in terms of, you know, what is really important with this whole idea of the types of solutions and whether they're consistent or inconsistent. Number 11, it says pictured is the graph of an inconsistent system. Fill in the blanks for this system of equations. Well, if we look over here and we can kind of, you know, maybe start to think about what type of a solution is this. Well, we can see that our lines are parallel, right? They are stepping one, you know, kind of the staircase is basically the same. And we can always see that if we just even picked 2 points here, we can see we went up 2 and positive 1. We could do the same here. We're going to go from a hash mark to another hash mark there. This is plus 2 and plus 1. These are the same slope, right? Obviously, one of them crosses the y-axis at -3. The other one crosses up here at positive 2, but our slope is the same, right? So this would be an inconsistent system, and our lines would be independent. Okay, number 12. Pictured is the graph of a consistent system. Okay, and fill in the blank for the system of equations. Well, remember, consistent system says there is a solution. We definitely have at least one solution, don't we? And you can see there's only one line here. So there really isn't. We know that there are 2 lines because it's a system. It tells us it's a system, so they're the same lines, right? So basically, these equations don't really look the same, but we can see that this one is just simply multiplied by 2, right? So if we multiplied this first one by 2, you can see that the second one would just be a 10 there. Okay, and lastly, shown below are the graphs of 3 systems of 2 equations. Which system or systems are consistent? Well, remember, when we're talking about consistent systems, we're talking about do they have a solution or not. This is all about the solution, right? Does it have a solution? Of course, if it does have a solution, then there is some sort of an intersection, right? Well, parallel lines don't intersect, but we can see that we have lots of intersections in number 2. It's the same line. And we have this one intersection here in 3. So we would say that 2 and 3 are consistent. In which system or systems are the equations independent, right? So independent, remember, means different lines. Okay, well, we can see right here we've got 2 different lines in number 1, and we have 2 different lines in number 3. We have the same line in number 2, so that would be a dependent system. All right, guys, so that is it for now for this video, and we're going to be talking about systems of inequalities in the next video to come. All right, see you soon.